All right, so as promised, we're going to take a little trip to Mars. We're going to start at Mars. This is on our website. I wanted to point out a couple of things. At the top of our website, you'll see under software, we have the 4 little chevrons with our little center your design, what, why, when, and where. What I showed you this morning, what is HyperX, is at the top. That's how you can get to that video. And then, of course, now we're doing the where. So let's get going. 190 million miles from Earth, Mars. NASA worked a mission to return soil samples back to Earth. On top of this rocket, you can see the Mars Sample Return Capsule. Our company worked on this project for 8 years, first with NASA Langley, and then the project shifted to JPL. Next, altitude of 239,000. This morning, I talked about the NASA Orion that we worked on here with NASA and the NESC, but we also did work on several of the commercial versions of the commercial crew modules. Also at 239,000, we worked with NASA Ames on their LADEE project. This was a environmental sample collector. It circled the moon for 100 days in 2014. And HyperX was used to resolve negative margins and get weight out for all the new load cycles that were issued. Moving down to 310 miles, we have Blue Origin's Orbital Reef Space Station. HyperX was used by both Blue Origin and Collier engineers for its design and analysis. If you hover over these little dots, you can see a little more about each of the projects. The second one here is, you'll see there's a vehicle attached to the space station. This is called the Sierra Space Dream Chaser. Its purpose is to return crew from space. It was designed with wings so it can land like a conventional aircraft. HyperX was used to perform architectural trade studies. We provided insights and sensitivity studies for structural weight to various of their design features. 62 miles altitude, we have the more of the space tourism area where we have Blue Origin's New Shepard rocket and space capsule. It's designed to carry customers past the Kármán line at 62 miles. The crew capsule carries 6 passengers with large windows for viewing space. And HyperX was used by both Blue Origin and Collier engineers for its design and analysis. A little bit closer, 54 miles. We're looking at the more space tourism, the Virgin Galactic, the reusable suborbital rocket. It has a wing design, as you can see there. It has an empennage with this feather system, which is very unique, and it's used to slow descent. It's carried to its launch altitude by Scaled Composites White Knight 2, and it's showed in this pop-up here. Then back to the Virgin Galactic vehicle, it flies into the upper atmosphere, powered by its own engine, and then glides back to Earth for a conventional runway landing, which is pretty cool. HyperX was used by both VG and Scaled for analysis and design. And later, well, tomorrow, actually, you'll hear Bell talk about they did the design and manufacture of the feather system that I just mentioned. They used HyperX for design and analysis, and we'll hear from them tomorrow. Next, at 36 miles altitude, we have the crew capsule reentry vehicle. We're showing here the Orion crew module's heat shield that I talked about this morning with NESC and Mike Kirsch. This one was very unique because of its intense structural and thermal protection design challenge that it gave us. A little bit closer to Earth, at 60,000 feet, we have Arion. It's a supersonic business jet that in 2020, the Orion Corporation unveiled their updated design for a 12-passenger jet reaching Mach 1.4 in Super Cruise with non-afterburning engines. But then in 2021, Arion shut down for business after 17 years. The AS2 was never built. However, its composite stiffened panel wing was highly optimized with hypersizer at the time by both Arion employees and Collier employees. 41,000 feet, we're looking at business jets here. I'll kind of cover business jets and commercial jets here. A lot of our applications, as you've seen, are composite. However, we also work with a lot of traditional metal aircraft customers. Both business jets and commercial jets are designed and manufactured with aluminum. This requires traditional analysis methods to account for their thin sheet skins, and they're mechanically fastened to the stringers. We do these traditional analyses for a lot of customers since it's more common. Next, we have the Space Launch Mothership, which I mentioned earlier. There's a little pop-up. I don't know if you can see the little dots. The little dots are the humans. That's how big it is. It was designed and built by Skilled Composites. It's called Stratolaunch, and it was the largest composite structure aircraft ever made at the time. Hypersizer was used again in the design of the analysis for the carbon fiber structure of its 380-foot wings. It's amazing. Moving down, I mentioned commercial jets already. Now we're going way down at 1,500 feet in altitude. We're looking at UAMs and eVTOLs. Startup companies in the UAM field are in need of all four of the HyperX little chevrons that we talk about centering the design. They need to work very hard to reduce weight because electric batteries are so heavy. It's very challenging. They need to shorten schedule. The goal for UAMs that they've set for themselves is 4 years entry into service. Average for general aviation is 7 years. And they need to improve producibility as they've set a goal of 10,000 aircraft per year by 2030. Pretty lofty goal. And certification on time, of course, is important. The DAC cycle, the design analysis cycle, has to be fast, accurate, and prove excellent traceability, since they don't have legacy methods in-house because they are startups. Oops, moving down a little bit, we have here the Bell V-280 tilt rotor aircraft. And of course, we have Bell speaking tomorrow. Spirit used our software for they've designed and fabricated the prototype fuselage ahead of time, and I'll show you the prototype right there. And to get there, they used Hypersizer for detailed sizing. Structural requirements included strength, stability, stiffness, and deflection limitations for pretty severe flight landings and ground load cases. And next, we are down to Earth. And we're going to go with reusable launch vehicles over here. HyperX has a long history of use by both government and industry use for design and analysis of launch vehicles. NASA used our software on all of their rockets since Ares 1, that means Ares 5, and SLS. Industry, such as Blue Origin, the New Glenn rocket, used HyperX and our Collier engineering team on nearly every piece of structure. That includes fuel tanks, pressure domes, interstages, intertanks, fins, strakes, dry structure, thrust structure, fairings, and more. And third, of course, our bikes that we all are so familiar with. We have Trek here, and Trek used us for both the design of the handlebar and the frame, and you'll see more about that with Ryan's presentation. Also at ground level, we have the SP80, which maybe you guys have heard about. It is trying to set the world record for sailing. In other words, no motor. It's all wind-powered. It's through a kite. And I think they've reached 56 knots so far, is where they are, and they are gunning for 80. That's why it's called the SP80. So we have helped with that design as well. Keep an eye on them. It's pretty fun. And that is our trip. So thank you for listening, and we'll queue up the next person.